Hi, my name is David. Today in inorganic chemistry, I'm going to be talking about calculating the effective nuclear charge for a given electron. When I say a given electron, I mean like a 1s or a 2s, or a 2s or a 2p. Now I'm going to start off by defining nuclear charge. That's simply the positive charge of the nucleus. It's equal to the atomic number. For example, hydrogen, it's got only one proton, so its nuclear charge is going to be 1. For oxygen, the nuclear charge is going to be 8. That's how many protons it has. Then we have what's called the effective nuclear charge. That tells us how much of that nuclear charge a certain electron experiences. You see, all the electrons are attracted to the nucleus. They all want to be near it. But they can't get too close because the electrons are repelling each other. That's why electrons have different energy levels. 1s, 2s, 3s. And so what happens is, the electrons that are closest to the nucleus, they experience the most nuclear charge. So they have higher effective nuclear charges on them. Whereas the electrons that are farther away, they experience less of that nuclear charge. So we say that they have a lower effective nuclear charge on them. Hence, we say that the closer electrons are shielding away the farther electrons from the nucleus. Alright then, so we've just described how the closer electrons shield away the farther electrons, and how that causes the farther electrons to have lower effective nuclear charges. Now let's get around to actually calculating effective nuclear charge. In this case, we'll be working with the 5s, 5p, and 4d electrons of a tin atom. The element is important because that helps you know the nuclear charge. So to find the effective nuclear charge, we use this formula right here. Since shielding lowers effective nuclear charge, then you can see why we would use an equation involving subtraction. So we use Z to show the nuclear charge, and that's equal to the atomic number, so we just go in our periodic table to find it. Alright, so cursor's over here. The elemental symbol for tin is Sn. So if I zoom in a bit, then I can help you see that the atomic number is 50. Hence our nuclear charge is 50. Now then, for the rest of this equation, we're going to find the shielding constant. The shielding constant we have to calculate using Slater's rules. And I'll be getting into that right now. But first, to start using Slater's rules, we have to understand electron configuration. So let's look at tin. It's right here. Now, electron configuration, you've probably done this in Gen Chem, but in case you're a little rusty, just going over it right quick. We have the 1s1 and the 1s2, so we would write 1s2. Then we have the 2s2 electrons right here, and the 2p6 electrons. So 2s2, 2p2, 6. Then we've got the 3s2 electrons here, the 3d10 electrons here, and the 3p6 electrons here. Now, usually when you're writing electron configuration, what you're going to want to do is write 3s2, 3p6, and then as you get more electrons, then these orbitals start filling up. But in the case of Slater's rules, what you want to do is just write it straight across. So it's going to be 3s2, 3d10, and 3p6. Now, tin's in the 5th row, so it's up to the 4th row before that. 4s2, 4d10, 4p6. 4p6. Alright. Now that we're in the same row as the element we're looking at, tin, we have to be careful. Because usually, when you're working with d electrons, what happens with the electron configuration, it's going to favor half-filled shells. For example, if we were working with, say, molybdenum, which has 4 d electrons right here, it would tend toward having an electron configuration involving 5 d electrons. Now fortunately, since we're working with tin, we don't have to worry about that tendency, so we can just write it how it is. So, we're in the fifth row, it's just 5s2, 5d10, and then we're only going this far because this is where tin is. So it's going to be 5p2. I'm going to type that right now. 5s2, 5d10, and 5p2. Okay, we've got the electron configuration of tin. Now, why are we doing that? Well, because Slater's first rule is we're supposed to write down the electron configuration. Now, here I write down in the order of n. That's just going back to how usually we would write down like 3s2, 3p6, 4s2, 3d10, you know, alphabet principle. But with Slater's rules, we don't worry about that. Now, Slater's rules are a way to find S. And S is a shielding constant telling you how shielded it is. Kind of give you an idea of how many electrons are in front of it, how much is being pushed away. So, with the first rule being writing down the electron configuration, now we have to group the s and p orbitals together. That's part of the first rule of Slater's rule. So we're just going to write some parentheses here. Nothing for this. Basically, that just means we put the 2s and the 2p together, and we have to move this over here because we have to put the 3s and the 3p together. 3d is in its own group, and we have to move this aside because the 4s and the 4p go together. 4d is in its own group. Move that down so it's easier to see. Then we have to put the 5s and the 5p together, so they're in the same group. 5d is in its own group. Okay, so we've completed the first part of Slater's rules, and that's writing down the electron configuration and grouping the s and p orbitals together for the same n. Now the second rule is dependent on the electron that we're focusing on. Going back to the original problem, we're supposed to look at the 5s, the 5p, and the 4d electrons. So let's start with the 5s electron. The second rule is the electron you are focusing on is not shielded by electrons to the right of it in this electron configuration. So let me bring this over here. Alright, so if we're looking at the 5s electron, that's in this group. It's not going to be shielded by 5d electrons because it's to the right of it. Think of it as farther electrons aren't going to shield it. If anything, it's shielding if anything, 5s electrons are shielding these electrons. But we're not worried about that just yet. Now, you'll notice there's two 5s electrons. Now, a 5s electron is not going to shield itself, But if there are two 5s electrons, then one of them is going to shield the other. Now then, number 3, the third Slater's rules. Now we get into looking at S, P, D, and F. So, again, we're starting off with the 5s electron. So we get to use this rule. For the 5p electron, we also use this rule. But for the 5d electron, we're going to have to be using the fourth Slater's rule. But I'll get back to that. So, the third Slater's rule is, when we're looking at ns or np electrons, this is how we find the shielding constant. How shielded it is. Okay, so for the 5s electrons, based on the Slater's rule, we look at the number of same n electrons. Again, we don't count these because it's in a group to the right, but we do count these because it's in the same group as the 5s. So the other 5s and then 2 of the 5p, that's 3 in all, electrons of the same n, times 0.35 from here. Then we've got the electrons of n minus 1. Again, n equals 5, so n minus 1 is 4. 2 from the 4s and 6 from the 4p gives us 8 in this group. Then we've got 10 from the 4d. And 8 plus 10 is 18. So we have 18 n minus 1 electrons. We multiply that by 0.85, as shown here. Finally, we've got the n minus 2, n minus 3, etc. The rest of the electrons. The 1s, the 2s, 2p, all these. So, again, the 2s and the 2p groups together, that's all 8 electrons in these parentheses. So 2 plus 8 is 10. 10 plus another 8 is 18. And then 18 plus another 10 from the 3D gives us 28. 28 times 1. That 1 comes from right here. Now, there is an exception to this Slater's rule, and that's for a 1s electron shielded by another 1s is going to be 0.30. But since we're dealing with 5s electrons, we don't worry about that. So, we've calculated the S to be 44.35. Okay, so now that we have S, we have enough information to solve for the effective nuclear charge. Remember, it's Z minus S, or 50 minus 44.35. We can finally answer the question. And the answer is 5.65. So to put that into perspective, the nucleus has a charge of 50. But out of that 50, this 5s electron is so far away, it's so shielded, that it only experiences 5.65. Next we'll look at the 5p electrons. Looking at the Slater's rule, we see that ns electrons and np electrons follow the same rule. And we also see that the 5s electrons and the 5p electrons are in the same group. So actually we're going to get the same answer. Just to show you, we look at that same n electrons. Again, this time we're looking at one of the 5p, so it's shielded by the other 5p. And the 5p electron is shielded by the other 5s electrons. So 1 plus 2 is 3. 3 times 0.35. Then everything else is the same. So when you're working through the problem, you know everything's going to be the same. So that, based on that alone, you know it's just going to be the same answer. Just going to be, as we calculated before, .35. Now for the 4d electrons, note that this Slater's rule does not cover d electrons, just s or p. Fortunately, we've got another Slater's rule, and don't worry, it's the last one. And that is for d and f electrons. So the previous rules were mostly based on n. We looked at n equals 5, then n minus 1, and then n minus 2, etc. But this rule is going to be based on the actual group. So the first rule is we count the number of group electrons in the same group. We're looking at 4d electrons in this case. Well, one of them is the electron of interest, so that means the other 9 are going to do the shielding. So for the 4d electrons, this part of S is going to equal 9 times, based on the rule, multiplied by 0.35. Note that with the 5s and the 5p electrons, we would have included electrons of the same n, but in this case we did not. The next rule, basically every single other electron that's involved in shielding shields by 1. So the 4s, the 4p, 4d, 3d, everything else shields it by 1. So instead of 28, we're going to have this stuff add up to 28, and then we're going to have 28 plus 8. Again, if you don't remember how I got 28, it was 2 plus 8 plus 8 plus 10. So 28 plus 8 is 36. Hence the number of all electrons in the previous groups is 36. We multiply that by the number 1, as shown here. So note how d electrons and f electrons follow completely different rules than the s and p electrons, due to how these Slater's rules were approximated. So the shielding constant is going to be 39.15. Now, note how 39.15 is less than 44. That means these 4d electrons are shielded less. You can think of it as them being closer, as like how I showed previously in the electron configuration. Hence, when we calculate the effective nuclear charge, since they're being less shielded, we're going to get a higher effective nuclear charge. So again, 50, and then minus 39.15 this time, which is equal to 10.85. So let's go over what we've done. We've defined the principles of effective nuclear charge based on shielding. We've covered the Slater's rules, and you're going to want to remember these so that, because you're not going to be able to look at them, and even if you could, that would spend time. Look at the Slater's rules for s and p electrons and d electrons. We haven't done f, but it's the same thing as d. After doing the electron configuration, found s, and then found the effective nuclear charge. For the 5s, it was 5.65. For the 5p, it was also 5.65. I haven't typed it yet, but same shielding, same nuclear charge. It's going to be the same effective nuclear charge. And lastly, we see how the 4d electrons, since they're less shielded, they experience more of the effective nuclear charge, like the 5 and the 5p. 50 is the nuclear charge, but out of that, it's only experiencing a small amount due to shielding. That shows you just how important shielding is. Alright, hopefully I've been of assistance. Have a good day.